All right, we should get started with this last lecture of the series. So today I want to sort of briefly tell you about the black hole information paradox. So we ended yesterday by considering sort of what goes into a general effective field theory, local effective field theory approach to black hole evolution. So basically we need to have first of all, we need to, of course, figure out what is the action of this theory. But in general, what we know is that it will include the Einstein-Hilbert action for gravity, some matter coupling, so it will include the classical theory, and then there will be some semi-classical or quantum correction terms that will be, in principle, an infinite series of ever higher dimension operators, but they are suppressed by powers of a cutoff scale that we introduce. And then as long as the local curvature scale is, so we have weak curvatures compared to the cutoff scale, and we have also, then we expect this effective field theory to be reliable. And then on top of that, we also need to select a set of Cauchy surfaces that avoid the strong curvature regions for as long as we can arrange that, and we're not allowed to do that in a way that introduces strong extrinsic curvature. So these have to be smooth surfaces as well, otherwise we can expect there to be we would expect a breakdown of the theory for that reason as well. And I showed you a simple construction how you would get a set of Cauchy surfaces for a classical, it was for a classical eternal black hole. That's, of course, not exactly what we want, but it's a simple construction, and it can be extended to the geometries that we're interested in. And so now we're going to actually assume that we have such a theory. It turns out it's not going to be all that important exactly the precise form. Of course, it is important to have the precise form if we want to make predictions, quantitative predictions of outgoing radiation, etc. But if we, for the sort of general considerations that I want to talk about today, it's mostly the fact that the assumption of an effective, local effective theory is really sufficient. And the setup that we want to start with is we imagine that we have matter initially in a pure quantum state. And so some diffuse collection of particles that's undergoing gravitational collapse. And let's not worry too much about how you would prepare such a state. Simply we'll assume that it can be done in principle. And then this system will undergo gravitational collapse. To a black hole. Of course, not necessarily some of the matter will go into the black hole, some will not. And but we know also that for this black hole, very quickly it'll settle into that's what the classical equations tell us, it'll settle into a sort of quasi-stationary state that actually in the classical theory, it'll actually settle to a stationary state which carries, there's very little information available about what made the matter. You will have basically the gravitational field of the black hole will contain information about its total energy, its total charge, and total angular momentum, but not much else. So whether this was a cloud of, gas in some cloud in interstellar space, or whether it was a collection of pink elephants that were falling in. There's no information about that once you're in here, right? So, and this is not necessarily a problem for the quantum theory. It just says, okay, we have still a pure quantum state, but part of the stuff that's inside the black hole is not something that's accessible to us, And whatever is outside is in general going to be entangled with what's inside. And so we will have limited information, but we can work with that. There's nothing fundamentally wrong with that. But then the next thing we need to think about is the Hawking evaporation. And in the semi-classical approximation that the semi-classical calculation that we went through, the outgoing radiation is thermal. And also, actually, if you look at it, it only carries information about these charges that I mentioned. So there's some outgoing radiation. Possibly there's a tiny little remnant left behind. We can't really predict what happens at the end of the process because we don't have control over the theory at that point. And this will have outgoing thermal radiation. And radiation. And that means it's in a mixed quantum state. Okay, so this process appears to have taken an initial configuration that we, by assumption, said was in a pure quantum state, and then we evolve through this intermediate state that involves a black hole, and we end up with a final state that's in a mixed state. And this is not something that can happen in quantum mechanics. If you have a pure state initially, then your evolution, your Hamiltonian evolution, will give you a pure state at the end as well. And so the question is, what went wrong here? Well, Hawking, when he originally pointed out this issue, suggested that we simply have to modify our fundamental laws of quantum physics, and we'd have to accept that unitarity would simply not be preserved once you include gravitational processes. And as soon as you have this problem, of course you're going to have it. There may not be a huge likelihood for pair-creating black hole configurations, but as long as there's any, you would have this evolution even in the absence of actually forming a classical black hole. All right. So I'm going to now formulate this paradox in a somewhat more precise way, and put it into the context of the sort of formalism that we have been that I've been developing in these lectures. And I'm going to do it in two ways. One is sort of an old-fashioned way of doing it, and the other one is more recent. So let's look at the first version here. And so there we have, let's first ask, what is the implication of having quantum mechanical unitarity? Well, sort of a very general feature there is if we have a system that is in some initial state in a pure state, let's call it psi I, and the final state is also pure. And there's a unitary matrix. So this is psi in, let's call this psi out. Is also a pure state. And it's related to the initial state by a matrix, unitary matrix, that we call the S matrix. Okay. So the S matrix is unitary. All right. Now what that means is that I can multiply both sides here by S dagger. Doesn't matter in which order I have this here. And it tells me that all the information, I can actually reconstruct the initial state by the adjoint of the S matrix. So it means that if I have, so the final state actually contains all the information that we had in the initial state, because it can be reconstructed in principle via the adjoint of the. So this is one thing that we have to, so if we're going to have unitary evolution, then we have to make sure that our final state actually satisfies this, right? Now, we're going to consider the evolution of the initial state forward using an effective field theory. All right? And we're going to make the assumptions that I listed before. So we assume that we have a local effective field theory, can be applied in regions of weak curvature. And to whatever precision we need, we would just include more and more terms that are suppressed by the cutoff scale. But it's important that for this general argument, the explicit form is really not needed. All right. Now, you have to identify suitable set of Cauchy surfaces on which to carry out this evolution. And then you would, perform some sort of canonical Hamiltonian evolution based on the whatever, that's appropriate to your effective field theory. And so that is going to, this evolution, of course, is going to include not only, so you would obtain the Hamiltonian from your effective field theory Lagrangian, it's actually going to include some both intrinsic curvature pieces and also the extrinsic curvature. That's why you need both of these conditions here. All right. And locally, from one Cauchy surface to another, this Hamiltonian will generate unitary evolution of states. And so we're going to see how this setup cannot actually coexist with this one. That's the essence of the paradox. And so what we're going to do here is we're going to draw our Penrose diagram for the semi-classical evolution. That looks something like this. Right? Here's my horizon. And so at some early time, before the black hole forms, I can have this space-like Cauchy surface here on which I define my initial state. So this I will call sigma in. Okay? So that's at early times. I'm also going to have a late time slice, which I will somehow like this. And that's going to be my, where I define my out state at late times. And the S matrix is supposed to relate state on this initial slice to the state on this slice, right? So we're going to assume pure initial state psi on sigma in. And now I'm going to take an intermediate time slice, which is one of these nice slices that I talked about yesterday that intersects the black hole. In particular, it, I'm going to label it by this point P. It actually crosses the event horizon at some point. Okay. And then by the unitary evolution generated by the effective field theory Hamiltonian, we can say that this will, so it evolves under to a pure state let's call that psi of sigma p. Okay. And this pure state has support both inside and outside the black hole. Right? And now I'm going to call the outside part of this Cauchy surface, I'm going to call external, and the inside part of it I'm going to call the black hole part. Okay? So it's inside and outside the black hole horizon on respectively. So far, so good. Now, these are space-like separated, these two guys. So the next thing we will say is that the observables, if I have local observables on sigma x, this part, they will commute. With observables on the space-like and so we conclude that is then in a tensor product so where these observables will act on these separate. Now, strictly speaking, I can't really do this. This effective field theory Hilbert space does not, exactly factorize. So this is a weak point in this argument. That it's sort of, and in the second version of the argument, I will not rely on this. Okay. So. But the argument then continues to say, well, okay, if we want to know what is the state on the outside part, on here, well, we have a pure state on the full slice, and we will simply trace over the degrees of freedom of this of this Hilbert space. That'll leave us with a density matrix that describes a mixed state on the external part, and that part will then evolve, modulo something that we don't really have very good control over here at the last gasp of the idea. But the gist of the argument is, though, that most of the information, if it actually is coming out, it'll come out in the Hawking radiation long before we get to the endpoint. So this argument should, and the failure to have a factorization is also associated with kind of, it fails locally at the point, where you cross the horizon. So perhaps, this argument could be cleaned up a bit, and we could actually sort of estimate that there will certainly be degrees of freedom that you would associate with being deep in the interior that you would want to trace over because you have no access to them, and that will lead to a mixed state. So the argument is not quite as clean as it looks here, but this assumption of factorization, of course, is something that we made already when we were discussing the Rindler story, because we assumed that the Hilbert space on the right Rindler wedge were actually, that we were in a tensor product Hilbert space. Now that is, I emphasized in that conversation, that discussion, that is a formal argument for exactly this reason, that this assumption of factorization is strictly speaking not quite valid. Okay, so, but let's just forge on. So taking a trace or partial trace over this guy, that results in a mixed state on the out. The external part, okay? And this cannot evolve, a mixed state cannot evolve back into a pure state. The evolution, for, going forward from here, we would still have our local evolution using the effective field theory Hamiltonian. And so we end up with necessarily a mixed state up here as well, which then cannot be a unitary evolution from here. So this is sort of in essence what the paradox is about. Okay. So the net result is that a pure state on has evolved okay. Now, all right, so this is this first formulation of the paradox. Let me make a simple note, though, which is that there is a sense in which this could all work, which is the following. If, for some reason, the nice slice state remains a product state, at all times. What do I mean by that? It means that that the state on this sigma p is actually given by a product state. It's not just a member of the, not just an element of a tensor product space, but it's actually a very special state, which is, if this is the case, then we can preserve unitarity if actually does not depend on the initial state. So what do I mean by this? Well, what I really mean by this is that if this part of the state that's sitting inside the black hole does not depend on what the initial state is, it's really saying that there's no quantum information actually enters the black hole. And then, of course, this is a unitary evolution of the initial state, which then goes on to be unitarily evolved. So that is basically a way to resolve this, is to say, well, if we can arrange it so that there is no information going into the black hole, then clearly the quantum information stays outside the black hole and we don't really have a problem. Now, well, this is quite nice. If you have a very, very large black hole, you might wonder, well, what's to prevent the information from going in? So, I mean, that's the essence of the paradox. Okay. Now, this could be achieved in different ways, and there's kind of radically different ways of looking at the problem. One is to say, well, this thing is actually not a smooth surface. There is really something quite that these quantum effects, the requirement of having unitary evolution will actually mean that the local sort of, you will not, it basically says that this quantum state here cannot be a Hadamard state. We said a Hadamard state was one which is sort of locally like a state that is evolving in Minkowski spacetime. There has to be something dramatic that happens here at the, and one thing that has been proposed is that this really will mean that there are, you've kind of, if you insist on this, is you're insisting that there is no entanglement across the horizon, right? This is precisely a state that is not entangled, right? When you have a product state, it's not entangled. And of course, as we saw, the Minkowski vacuum, this is practically a flat spacetime if it's a large black hole. And we saw exactly that the Minkowski vacuum was very much an entangled state of different Rindler modes, and the same of you would expect here if this local effective field theory really holds. But if you insist that there is no entanglement, it means that this does not look at all like the Minkowski vacuum, and this is what has been called sometimes a firewall. So basically, because of these quantum effects, for some reason, this simply becomes an impenetrable. Well, this, of course, is a major violation of the equivalence principle. You do not really expect. This would mean that no observer can enter the black hole. Nothing will actually go in any. So that's if you're going to insist on locality. There's another way in which you could implement this idea, and I'll come back to that and later on, and that is basically this idea of black hole complementarity. And that is basically says that if you're actually thinking about what outside observers or observers up here, what can they actually see? Well, they can see radiation coming out. They don't really see anybody entering the black hole because of the redshift. I mean, this is something that you probably saw and was discussed in classical GR. If you have a black hole, an observer is falling in. There is this funny thing that the outside observers just see them get slowed down. They see the redshift, and in classical theory, it's an infinite redshift, and they never actually go in. I mean, this is sometimes called the frozen star picture of a black hole. And before these developments in around 1960 by Kruskal and Zekaris and others. This was, sort of a contender for what is the physics of a black hole. That stuff, it just sits there, and there really is nothing. There's no meaning to the interior solution. But that I think we've settled that is not the case. I mean, you can just do this is just a coordinate singularity. You can extend through it, and so if you're actually the observer who's going in free fall, you just pass through this, and you will end up at the singularity. So there clearly was this already at the classical level. There's a very different view of what's going on here. The outside observer would say, okay, you actually, as far as I can tell, you never go in. Now, what changes once you include the Hawking effect is that, well, actually, the observer doesn't really go in, and that there's no infinite redshift here. What you see is Hawking radiation that comes out, and it's, of course, it's redshifted. So when it starts out from near the horizon, it's going to be high energy radiation. And so the model that you might use, and this is a model that was proposed by, it was actually it's a useful model from astrophysics, is that you basically replace, you postulate that there is a time-like surface here, which is called the stretched horizon. Just outside, you place it like sort of postulate that there is an area, time-like surface here that has an area that's equal to the area of the event horizon plus 1 Planck unit. That's all it takes to make sure that you're now on a time-like surface. And then the claim would be that whatever you see out here can always be modeled by having basically this. And now, of course, this is a surface. It's a time-like surface very close to the horizon. That means if you were an observer sitting at that surface, you would have an enormously high fiducial temperature. In fact, you have to think of this stretched horizon as surface. If we make it literally 1 Planck unit out, it's going to have a Planck temperature. Okay? And then, now of course, when people were using this in astrophysics, they put it further away, and then the temperature was lower. Actually, for this, so this is what's called the membrane paradigm of black holes. You would actually replace the black hole. If you're going to do computations that involve the black hole interacting with some environment, could be an accretion disk, could be a binary partner. And then the claim is that when you're solving classical GR, you can actually do this. You can replace the black hole part here with this surface. You have to endow that surface with some sort of macroscopic properties, some viscosity and conductivity and some, and then if you do that, you can actually solve. Then you don't have to solve the Einstein equations in this region. It sort of is a useful computational tool. And they had already said, this is Kip Thorne and others, that okay, this is a useful thing, and from the point of view of outside observers, you might, you can really replace the black hole by this surface. But they were, of course, quite cognizant of the fact that if you were falling into the black hole, there should be no surface there at all. You should just fall in. Okay, so there's a sort of duality in the description. Now, so what we suggested, this is with Susskind and Aglum, we suggested that, well, we should actually think about this stretched horizon as a, and by the way, the astrophysical stretched horizon has a temperature, which is actually given by the fiducial temperature of wherever you put it on. And it has thermodynamic properties, and we suggested that, well, we should really think of that thermodynamics as coming, that it comes from the statistical mechanics applied to some set of degrees of freedom. So we put 1 degree of freedom per Planck area on here. We were not able to, and we're still not able to tell you exactly what those degrees of freedom would be, but they have to satisfy certain properties. They have to be, their interactions have to be non-local and chaotic, and you have to make sure that whatever falls onto this stretched horizon gets thoroughly scrambled rather rapidly. And then you basically have and in this model, the Hawking radiation is just the thermal radiation coming from this surface. And because of the deep gravitational well, most of that thermal radiation will actually fall back. It's really only the low angular momentum modes, S waves if you're in a scalar, or P waves, that actually make it out. and give you this low energy radiation. So then you'll have a slow process where black hole slowly disintegrates, and then your picture would be that, well, whatever happened to your infalling observer, you can't really see it clearly because it's so redshifted, but in principle, if you detect all the radiation that comes from the black hole, you should be able to reconstruct what actually happened, and it would be that they got destroyed hitting this. So this stretched horizon is also, in that sense, it is exactly what you would call a firewall. Okay, but at the same time, we have to insist that if you're in free fall, just like in astrophysics, you don't see this stretched horizon at all. So this, of course, sounds very dubious. It is highly non-local, clearly, because, you know, but the point is perhaps that even though you have a low energy observer going through here, and they should, the question is really, can you actually think of any way which an observer who's falling in here could communicate the fact that there is nothing in particular happening, and to contradict the observations made out here that you are seeing this high energy environment here, highly redshifted. And so what you can do is you can try to construct various Gedanken experiments, and I guarantee you that every time you do that, at some point in the analysis, you will find that actually to compare notes between observers who are disagreeing about what's going on, you have to make some assumptions about very high energy physics. And I'll give you an example in a minute, but this is really a pattern. So even though we claim that we're doing effective field theory here on locally smooth Cauchy slices that avoid the strong curvature regions, so effective field theory really shouldn't be, giving us any trouble. What you will find is actually these, although locally quite smooth, these nice, they're globally maybe not so innocent. What happens is that if you, for example, were to take a normal vector to, or take a normal vector to your nice slice somewhere here close to the horizon, and you parallel transport it out, then you will find that it's what was a low energy, let's take, I mentioned it yesterday, the 3 momentum, for example. You take that, and you will find actually when you parallel transport it out far away, that there's an accumulated redshift there that will tell you that actually, so there are large numbers associated with these slices when you think about them, not locally, but actually the global structure. So there's, so that would be the claim, is that there really is, I maintain that there is no way you can actually prove me wrong on making this assertion that there is a description appropriate for outside observers where you have radiation coming from the stretched horizon, and while at the same time saying that a local observer will actually not see anything. Because in doing so, you would actually, not staying within the, not without making assumptions about some, Planckian or transplanckian energy, which we're not justified in doing because we don't really know what, for that you would need quantum gravity. Okay. Go along with me here for this. Then, of course, this is an example where there is no information going into the black hole from the point of view of this outside, because our entire description now, you can view this as a boundary to actually, this is now a globally hyperbolic thing you can just evolve. And so what you need, of course, is to then, you would have to also describe the degrees of freedom that are on here that are actually interacting with the outside. So I'm not saying this is simple, but in principle that could work. Okay. So, all right. So let me give you the other formulation that doesn't rely on this factorization property, but it actually involves analyzing one of these Gedanken experiments that I. Where? Yeah. Well, your problem here is that already down here you had a mixed state over here. Okay. Well, then you're assuming somehow that you can communicate superluminally, get the information out of here out. That is certainly one way to do it, but that is also quite non-local. Yes, and I'm telling you, if you're using local effective field theory, they can't get out. That's the point. Right, absolutely. No, no, sure. I mean, that is the issue here. If you have some non-local dynamics that will actually let you get things, then you do this. But that is not local effective field theory. That is some non-local effect in quantum gravity. Yes. Now, I think the point is that you're already in trouble long before you get there. Okay. No, no, the effective field theory will clearly break down here, for sure. This is where the black hole is it's gotten down to practically a Planck scale, and there will be no local effective field theory that describes the endpoint. Sure, if you have, but all I'm saying is that you are going to violate the premise of a local effective field theory. And that is what the information paradox is. I don't, I think most people who are in this business, at least particle physicists, they will say, okay, quantum gravity will fix this somehow. Uh, and it'll do it in some non-local way. I think a very good indication of that, and I was coming to that later, is that if we use gauge gravity duality, it's kind of manifest. We have a dual description of everything that's going on, which is manifestly unitary. But of course, the bulk, the actual duality map, the ADS-CFT duality map, is anything but local. It is extremely non-local. So, but we get back to that in the second lecture, second half. Absolutely, they're emitting the radiation that goes out. Yeah, sure. And that's the model. Okay, yeah. Um, and I mean, there have been attempts to try to model this by putting, a set of qubits, the appropriate number of qubits to account for the Bekenstein-Hawking entropy. And they need to interact all with each other, but they have to be what's called, so they're not local. So every qubit can interact with the other qubit, but not with too many at the same time. These are called k-local interactions, where k is the number of qubits in each interaction, and that k cannot scale with n, the total number of qubits. It has to. And if you get that, then you will have dynamics that's conjectured to be chaotic and is what's called a fast scrambler. And it's, if you allow all the qubits to talk to each other simultaneously, of course, then you can do things. Then you can just scramble things instantaneously, and that actually is not. That's too fast, if you like. So there are some ideas. Certainly, I'm not going to go into that, I think. But let me just do the second formulation of the paradox, and then we avoid some of the um, this issue of factorization here, and we'll still run into a problem. So this is a Gedanken experiment that is sort of an elaboration of one that we already discussed, shortly after we proposed this stretched horizon, which was there we figured, well, okay, if you can really read the information that comes out in Hawking radiation, and that information starts coming out after the so-called page time, um, then you would just sit outside the black hole, you would collect a bunch of radiation, you would read whatever information that you're after from that radiation. You would also have somebody carrying, so let me just describe let me just go through it. And so we're going to try to use the fact that in some sense, the quantum information, if it's coming out in the radiation, and it's also going into the black hole, we've done what's called quantum cloning. Now, quantum cloning is something that you cannot do in ordinary quantum mechanics, so it should lead to some issues here. So if you assume the information comes out, you also assume that the local effective field theory is valid, then you will actually be able to sort of do the same measurement twice. You can clone the information that would lead to contradiction. I'll show you explicitly how that works. And then the question is, can you actually do this experiment? We'll come back to that. So this is version 2. And so we're going to establish a contradiction here. So we're going to hit, for this one, we're going to assume that effective field theory is valid on nice slices. And we're going to carry out a Gedanken experiment. But maybe we should take a break first. I think we have, let's take a 5-minute break, and I will continue afterwards. And then what I'll do is I'll give you the second formulation, and then I'll discuss, sort of list various resolutions of this. I'm already started talking about one of them, which is this black hole complementarity. Firewall is another one, but there are more. There's no lack of creative ideas here or opinions. But okay, let's take a break before we go there. I doubt it. Better? Yeah. So now I'm going to give you another formulation of this paradox, which sort of, it is kind of an elaboration on a Gedanken experiment proposed by Suskind and myself back in '94. And then this new iteration of it was in a paper with David Lowe that I wrote in 2007 or 8, I think. So it's been around for a while. And so here we're going to do the following experiment. There are 3 characters participating in the experiment. It's we call them Alice, Bob, and Charlie. And the first step in the experiment is that we're going to prepare a singlet pair, so an entangled pair of spins. Now, possibly these should be a pair of isospins, because of course spin is an angular momentum. It'll have a long-range field, and so we don't want that to be. So we imagine that we can just take a pair of qubits, possibly, with that we can do local measurements on. Okay, so that's the first step. Then we separate the pair, okay? And Charlie is instructed, so that's C. Now it takes one member of the pair far away from the black hole. And then at a previously agreed upon time, okay, he carries out a measurement. But Charlie carries out a measurement that, so C will measure either the X or Z component of this spin 1 based on a coin toss. So basically, Charlie takes their spin out, carries out a coin toss, so neither Charlie nor Alice or Bob could know beforehand, before he does this, whether he measures the X or the Z component. But he does one, okay? Now, step 3 is that Alice enters the black hole. At the time of C's measurement, and this is, of course, in nice slice time. So both A and C are using the same, they've agreed on some foliation of the space-time, and they're using the same time variable, okay? And as soon as she's inside, promptly measures, let's say, the Z component. Of the other member. So she takes the other member with her. So this is where we measure spin 1, and then Alice is measuring spin 2. Okay? Now, Bob, on the other hand, hovers outside the black hole on this same time slice. Okay? And keeps track of all the Hawking radiation that comes out. And don't ask me how Bob does this. I mean, this is just, we're going to assume that he can do that. Okay? Now, of course, if this really is a quantum state that has been prepared, really to do this, you presumably need a whole collection of identically prepared quantum states. You redo these measurements and you do statistics and the usual thing in quantum mechanics. But let's assume that they can do that. Okay. Now, and once the information starts coming out, Bob can presumably infer the state of spin 2. If the information is all in the Hawking radiation, then they can presumably measure that information. They're using the nice slice time. So we have this, we assume that they've done this nice slice thing, and so we're actually following. So of course, Bob would have been just being out here. He would be carrying measurement. The point is that there exists a time slice on which, having done all those measurements, there's all this stuff coming out. Alice can do her measurements. This is all happening at the same time in that set of foliation of the pool. Okay. Now, so he keeps tracks of all the outgoing Hawking radiation, and he measures sort of the Z component of what you might call the quantum clone of number 2. So basically, he's measuring what is the state of what is the spin Z component of the spin of number 2, and so basically he's doing the same measurement as Alice, except he's doing it using the Hawking radiation, because that contains all the information. We're assuming that we're getting all the information out, and we're going to establish a contradiction with that. Now, once he's done that, Bob enters the black hole, what's left of the black hole, and receives a message from A that allows him to compare results. So A, as soon as they enter the black hole, they carry out their measurement and they broadcast the answer. Now, of course, the answer cannot be broadcast to Bob outside the black hole because you're already inside. But the idea is that the signal will travel out here and Bob can actually pick it up when he comes in. Okay. So let's see where that leads us. Well, and then the claim is that if A and B disagree, so they're measuring, the local measurements they're doing, they're space-like separated, so they commute. The measurement operators commute. So these are two independent measurements, so they can. But if they disagree on the answer, the point is that if C actually measures the Z component, then we know by because of the nature of the singlet state, that this measurement is then going to have the opposite, a measurement of the Z component is going to give you the opposite answer, right? Well, if I do this indirect measurement through the Hawking radius, that is also going to have to give me the opposite answer. If, on the other hand, C measured the X component, it tells you nothing about the Z component, right? And then these two guys are actually, they're equally likely to get either answer, and so they might disagree. And if they do disagree, if Bob gets a message that disagrees with the answer that he got, then he knows that C must have then measured the X component and not the Z component. Then C must have measured X component. So what we're finding then is that there's a finite probability for Bob to actually discover what C did, and C could be a light years away in preparing this. So then you would have a causal. So normally when you do EPR measurements, it's true that they are anti-correlated, but there's no way to communicate. You don't learn anything by that. But now I've set up this setup because I duplicated the information, there's a finite probability that B can actually discover what measurement can determine what measurement that this guy actually measured the X component, and that of course violates locality or causality, sorry. Not all. He needs to contain a lot of Hawking radiation. This is going to be part of the resolution of the, why this is not an experiment that, that is where the Trans-Planckian physics comes in. So let me get back to that. We have to ask basically how much Hawking radiation do you have to collect before you can expect to be able to know anything about what's going on in the black hole. And that turns out you have to wait until the page time. That is in fact the definition. Okay. So we'll get there. So basically, we're seeing an acausal signal from, so that's an acausal signal from C to B. Okay, and that, so we've basically turned this EPR correlation into EPR communication, and that is not. So why is this not something I need to worry about then? Why is this not a demonstration that there's a paradox here? Now, That has to do with the fact that, and I think I will just do this very qualitatively, but if you have a unitary, if you have a system, quantum system that is in a pure state, and you can think of it as combining two subsystems. All right. So this was the problem that Page considered. Imagine that you have a system in a pure state, and it's a typical pure state. So it's not, you imagine you have some fairly complicated, like any macroscopic system, of course, would satisfy this. You have a complicated system that's in a typical pure state. So a state basically that you would have, a state that you would imagine that you have a state that has some macroscopic properties like energy and maybe angular momentum or something, and then you would simply sample your you would randomly pick among the Hilbert space that satisfy that macroscopic constraint. The Hilbert space is a huge space, and so you're doing basically he was using the Haar measure on the set of unitaries that describe normalized quantum state is basically a if you have a large number of degrees of freedom and you have a normalized quantum state, basically tells you the only constraint that the normalization gives you is that the well, you can do a set of unitary transformations that don't change that don't change the normalization of the state, and among those you just pick one at random, and that was what he did in his computation. And then he asked the question of, okay, now I have a subsystem. One of them has let's say I have I'm talking about qubits. I have a capital N number of qubits, and then I take a lowercase n subset of those qubits, and I calculate the entanglement entropy of the, I'm in this pure state. I form a density matrix. It's like what we were doing with the Minkowski vacuum and Rindler, and I then trace over the degrees of freedom of the larger subset system, and I ask what is my Neumann entropy of the density matrix that results for the smaller system, and I will find that this is what Page showed, is that in fact, this Neumann entropy will take its maximal value. It will be that of a thermal state, up to a correction that goes like some inverse power of the dimension of the Hilbert space, which is a tiny number if you have a large number of qubits. So that means that if you're in this, if you are actually working with, if the degrees of freedom that you have access to is a smaller subset of the two, in the then you actually have no information. Basically, it's as if you just had a sort of thermal state. So you cannot actually learn anything from the early Hawking radiation that comes out. Now we think about our subsystem as whatever it's a black hole that we assume to be in a pure state. Then we start getting Hawking radiation out, and that is going to be just a few degrees of freedom to start with, and that is therefore very much the subsystem here. And it's not until you have reduced the number of degrees of freedom of the black hole down to half of what they were before. And so just to sort of keep track of numbers, we have a black hole that has some area. Its area is gives you the Bekenstein-Hawking entropy, right? And that entropy, if you want to have a quantum system that has the same number of states that entropy represents, it just tells you how many qubits you would have, and it's roughly 1 qubit per Planck area of the horizon. And then, as long as the if we ask what is the entanglement entropy of the subsystem as a function of the size of the subsystem, right? So that's here we have n, we have a total number of, and so here's our capital N here. And then really what the Page result was that, well, this entanglement area is of course very small when I have a very small number of n, qubits, the maximal, and then it'll simply grow. And it'll keep growing until I get to the point where my subsystem now has more than half the degrees of freedom. So this is n over 2 here. And then it actually has to start coming down. Now, that's because now the other system is the smaller subsystem, right? So its von Neumann entropy has to be maximal. And then because I'm constructing all of this from an initial pure state, I know the von Neumann entropy of the two states is actually equal. So this tells you that you have to, the entropy will go up, but then it will start going down. And this is the statement that the fact that it returns to zero is, of course, that once you're back, once your subsystem includes everything, that is, you only have outgoing Hawking radiation, well, then that should then be in a pure state, because the black hole is no longer there to be entangled with it. So this is the famous Page curve. And for a black hole, this means this point here is where the area of the black hole has reduced to a factor of 2. Okay. But if you ask, how long time does that take? Well, the black hole has a lifetime that goes of order m cubed. And you can easily see, of course, that the Page time, which is the time at which we emitted this much Hawking radiation, is parametrically also m cubed. It'll be m cubed, over some time divided by, it's a lifetime divided by some number of order 1. Okay? But we also know that these nice slices, they are perfectly fine until much later. In fact, they're perfectly fine until we get to be very close to the end of the black hole evaporation. So they should, in principle, you should be able to have a nice slice that extends beyond the Page time. And then, so therefore, Bob will at the very least have to wait until the Page time before he can learn anything about this spin that, and maybe it'll take longer, but it's a lower bound, okay? And now you ask, okay, so Bob waits of order Page time, then jumps in to get the answer. And of course, the problem then is, if you do the Schwarzschild geometry, is that Alice has to, be absolutely, be extra. Well, takes imagine that Alice is a very good and she does the measurement and sends out the signal in a Planck time, okay, or maybe 10 times the Planck time, okay. Clearly, she's not going to be faster than that. We're not going to, because then she's not a low energy observer. But let's just, for the sake of argument, say that she sends the signal 1 Planck time after, and then you can ask, how long can Bob wait, and in such a way that that Bob will actually see this message before he actually of the Schwarzschild geometry, you can easily check this, is that the time that Bob can actually afford to wait is actually nothing like the Page time. It's actually more like what I call the scrambling time. So basically, if I take an observer whose proper distance inside the horizon is 1 Planck length, I look at their future light cone, so anything they can affect, right? And then you will find that actually nice slice that will intersect this, the last nice slice that will intersect this is a time of order m log m. After so there's absolutely no way that Bob could actually do this. So that is what I was telling you. These Gedanken experiments, when you really start analyzing them, you will find that there is always some assumption about trans-Planckian physics, and in this case, it was enormously, it's actually, the time here would have to be e to the minus short time. And even if you could do that, then the energy that's, if you encode a signal of that time, is that such a, you would need an energy of order e to the m. So Alice would actually be a much bigger black hole than the one you started with. So that's so it just clearly cannot be done. Okay. And so but if, on the other hand, I'm simply not worried about these things and I think about local effective field theory, there's no limit on if I think about local effective field theory, there's no limit on what I I would imagine that I can do this. So this is just showing you that the effective field theory is breaking down it in this problem. Okay, so these are two ways of establishing a paradox, and then I'm kind of resolved it right away because of what I told you about the impossibility of doing the experiment. But let's think about other resolutions that have been suggested. Let me just go through a list here to give you a sense of there's a lot of work that has been done on this project. And, of course, one could easily give a whole other week of lectures, or probably more than 1 week, on the various ins and outs of this information problem. But let me just give you a little flavor. So now the first one, of course, was when Hawking first proposed this, is that there really is non-unitary evolution. This is also called information loss, so that you would actually have. And this was Hawking already in 1976. Basically, Hawking suggested that once you include black holes in your gravitational effect, you will simply have to rethink this whole notion of an S matrix. And he tried to do that. He generalized, he proposed a set of, you would call it generalized quantum mechanics, where instead of having an S matrix that related states, he had this thing that was called the superscattering operator that related an initial density matrix to a final density matrix. And this was a formalism that then allowed pure states to evolve into mixed states. Now, this was criticized by a number of people, but in particular, there was a criticism that criticized the particular formulation of Hawking. This was Banks, Susskind, and Peskin. That it is true they made some technical assumption, but they showed that under that technical assumption, this generalized quantum mechanical evolution that Hawking had proposed was actually equivalent to taking an ordinary quantum mechanical system and coupling it to a random source. And the random source had, strength 1 in Planck units. And if you did that well, then you would, basically your conclusion was that the problem was a phenomenological one, that the ground state or the state of this system was actually not empty spacetime, it would be some thermal state at the Planck temperature, which is not what we see. So, but there have been both. Question is whether that technical assumption they made can be somehow evaded, and or maybe there's some other formulation of non-unitary evolution that could be developed. So there are still some work being done in that direction, and this is certainly a logical possibility. Now another interesting one is called black hole remnants. This is Aharonov. Well, there are two types of black hole remnants, of course. Small ones, where you assume that you can do semi-classical physics until you're getting close to the Planck scale, and then all bets are off and you might be left with a remnant. And the suggestion by Aharonov et al., Kasher, Nusinov, this is 1987, I think, yep, was that this Planck scale remnant would actually carry all the information about the initial black hole, and therefore, in this picture, you would simply, whatever entanglement this state had with what was inside, it will now just be with this black hole remnant. And the overall system, remnant plus outside, would therefore be in a unitary state, be in a pure state, sorry. Now there was an elaboration of this by Banks and O'Loughlin. Which was in 1993. Now, the problem with these Planck scale remnants is, if you think about it, there has to be a distinct remnant state for every possible initial state. So you can imagine a black hole of some initial size. It has of order e to the area of the black hole, different number of different states, which is a huge number. And all of them would have to be represented by a different remnant. And it gets worse than that because the initial mass in your theory can be arbitrary. So you really literally need an infinite number of Planck scale remnants. Okay. So you would have an infinite density of states at the Planck scale in the theory. And then now you can start thinking about any quantum mechanical process. Think about, you know, E plus E minus scattering. Okay. You can do perturbation theory there. Now we usually do not worry about, you know, pair creation of black holes as a contribution to this. Sure, it's a gravity is and electrons have energy, so they will couple to gravity. So there would be loop effects where you would pair create these Planck scale remnants. Of course, a tiny amplitude for any given one of them, but that doesn't really matter if you have an infinite will diverge. So this actually will lead to, again, rather severe phenomenological problems in basically any physical process that you can imagine. Okay. So that's not really viable. Okay, so what about big remnants? Microscopic remnants. Well, this was suggested by Steve Giddings. Now didn't really, in 1992, he was suggesting this more like a logical possibility that there could be some subtle physics that would actually stop the evaporation rather rapidly, long before the page time. And then you would simply be left with a big object. Now, of course, you would have to then understand what is it about the physics here that actually prevents the evaporation of the black hole. That was sort of left unclear. But this is also of course, this would certainly resolve the information paradox because there really wouldn't be any, you would just have this large object, but it would certainly not be something that's predicted by semi-classical gravity or classical gravity, because you would somehow have to see either, well, would have to, in his case, he was interested in some then quantum gravitational effect that would actually stop the evaporation even when the black hole was quite large. Now, there's a modern version of this, which you might pigeonhole here, and these are called black hole mimickers. And there's a lot of research being done these days about this notion that maybe just black holes are actually not formed at all. Maybe there is some physics that we don't understand that actually prevents black holes from forming in the sense of having so this would mean that that you could actually have dense objects that are non-singular, do not have a horizon, do not have a central singularity, but can actually, unlike neutron stars, which we basically know cannot have a mass bigger than a few solar masses, make it tens of solar masses doesn't really matter because we know there are objects much more massive than that out there. Yep. No, I mean this is coming on my list. So um, now how it get? I think scalar here is maybe unlikely because it's well, we don't really have long-range scalar fields, at least that we know of. But there has been this notion that maybe the information is encoded into some, they called it, I think, soft hair. So these sort of so that there is some track of whatever went into the black hole. They leave some imprint on very low degrees of freedom at the horizon. This was suggested by Hawking, Perry, and Strominger about 10 years ago. I think There are some issues with that scenario in that their computations were entirely, they were doing classical gravity. And it's, I think, it was not clear that they would have enough degrees of, have enough, you could keep track of the required number of degrees of freedom once you turned the Newton's constant on, if once you started, sorry, Planck's constant on. And, but I think the jury is out on whether that is a viable thing. And also, they didn't really tell you of a mechanism how that you could leave some imprint on the of the ingoing matter on the horizon. How do you actually convert that to outgoing correlation correlations in the outgoing Hawking radiation? That's not saying it's impossible, but at least that is still to be supplied in that. Information. No, I think it's fair to say that they don't tell you that. No, no. Yeah, I think so. Now, Malcolm and Andy might disagree, um, but at least I don't know that it does, right? Now, these black hole mimickers the idea is that somehow something will actually prevent this black hole, that there really will, that gravitational collapse will actually leave an object behind. And this comes in many forms. This comes later in my list, so maybe I'll get back to it there. But one might call those black hole remnants. They're actually not even black holes. They're just, now, one way that you could have a macroscopic remnant is if this firewall proposal actually works. This is Almeri. 2012. This is Almeri, Marov, Polchinski, and Sully. Sometimes called AMPS, the acronym for that. I think I would classify that sort of as a macroscopic remnant. And this is just saying that the there will be no reason to be sending off Hawking radiation if there's really a singularity on the horizon. Okay. Now, also in this category, I might put in things that this is when you have a de Sitter interior. Okay, this is goes back to Mukhanov and Brandenberger. And that would have been 1991. So here the idea is that, well, maybe there is actually, the stuff goes into the black hole, but it doesn't actually end at a singularity, but there's really an interior geometry that is, so concretely what they did is they looked at a model where they said, okay, we don't really know physics beyond the Planck scale. Perhaps there is something that prevents curvature to become ever stronger than some cutoff, okay? And they could do that by proposing sort of a little bit weird matter theory, which basically imposed a constraint on the Riemann tensor that the Kretschmann scalar couldn't go beyond certain value. Okay, and if you do that, you can still try to solve the field equations. And what they found that instead of getting a singularity, because that's now forbidden, what they found is that there was kind of this was, if you like, a wormhole into there was another asymptotically de Sitter region. So there's like a de Sitter universe that sort of springs from the inside. It's causally disconnected from our universe. So this is sometimes called a baby universe. And the point was that this would simply carry off the information. Now this leads to all sorts of problems of its own. You have to then start thinking about a multiverse theory where you are trying to do your quantum mechanics on a this is sometimes called third quantization. It was quite popular in the early 90s. Doing quantum cosmology, and let me not go into that in detail, but it is again one of these things that has been, I don't think this has been proven not to be the case, but there are certainly issues with it. All right. Now comes to, we come back to my own favorite, which is that the information comes back out. Um, and that the problem is with the local and one suggestion is this. So this was very early on championed by Don Page. He basically said black holes should be no different than any other objects. Stuff goes in, and then just like, we can compare this process of black hole formation and emission. Let's take a more conventional way of losing information. Imagine that you had taken for some reason people always want to burn books. So let's take a dictionary and let's set it on fire and ask what happens to the information. Well, in some practical way, obviously we lose information, right? But there is a sense in which I think we all would agree that there is some Hamiltonian evolution that underlies this. We have a Schrödinger equation for the whole process. And all the information can, in principle, you should be able to read the book by just making careful observations of the outgoing thermal, apparently thermal radiation and the smoke and the stuff that goes out. And and then you would have, and this is what Page said should also be true of black holes. He didn't give I mean, he was aware of the fact that he didn't really know of a mechanism for this, but he was simply insisting that there should be some subtle and this is true in the burning book case as well, that you have to sort of establish some rather subtle correlations between early radiation and late radiation. You need the whole, you need to keep track of all the degrees of freedom in order to be actually able to recover the initial state. And importantly, of course, what you do know about this, that once you've burned the book and the information is no longer going to be in the book, it's all gone out. And the same thing here is what I was saying here. One way to resolve this is just to make sure there is no information left in the black hole and it all goes out. And so this stretched horizon idea that I was telling you about, that kind of is a way it's a model to achieve that. And now we have, now 't Hooft also was of this opinion, and he tried to simply solve the technical problem of figuring out the actual S matrix. And he wrote a series of papers doing that. Those were, again, technical issues with those for sure. Our work goes under this is called black hole complementarity. Complementarity was because there were these complementary views of what was going on by the asymptotic observers who would claim that there is, the unitarity is of course always just a question of what happens. You think of this as a scattering experiment. You start in some initial pure state, you have a final pure state, and there's a unitary scattering. You never need to invoke. The problem is when you also insist that physics makes sense for somebody falling in, right? And we claimed that we could really have our cake and eat it, in the sense that the stretched horizon picture was going to give us everything, unitary evolution going out, somebody falling in would really not notice it. And if you try to prove us wrong, we would always say, well, you've made some assumption about Planck scale physics. And that was not just a cheap argument. It really is suggesting that this resolving these issues cannot be done in the context of a local effective field theory. That's the point of that. But this is certainly not, you are giving up locality then in a very strong way. And maybe the best way to illustrate that is that, you can think about important events in our lives. There are two singular events in everybody's life. It's when it begins and when it ends, right? And here, you would now have, and what we're used to in general relativity, and one fact that it's a sort of space-time physics, is that the local event is an invariant concept. People may disagree on the the cause on which events happen at, on the time ordering of different events and such. But in GR, the local event, that's something that people would disagree, agree on completely, is that event where, the observer's life comes to an end would be a unique answer. But that's not the case here, because in the view of the outside observers that are used, they would say that the observer, unfortunate observer who's going in, never makes it through the horizon and is actually comes to an end at this stretched horizon. On the other hand, the observer who passes through, in our view, would then actually not really have any problem until they get too close to the singularity. And as the black hole can be arbitrarily large, this is actually it's an arbitrary degree of locality. So we have certainly given up locality if we go down this path. And so this was Susskind, Self and Uglum, 1993. And there was a simultaneous paper by Keim, Verlinde, and Verlinde with very similar ideas. 1993 also. Now, sort of on a very different note, but also I would, assuming that this is a unitary system and more or less standard, there was a parallel problem was studied by Maldacena. These are eternal ADS black holes on very long time scales. Certain correlation functions, if you just use classical gravity, would fall off with time, and whereas if it really is a unitary system, they're on extremely long time scales. They cannot go below a certain value. So this was 2001. There's also the final state projection, which is I think you could say that's just solving the problem by fiat. This is Horowitz and Maldacena. 2003. So there they simply say, well, actually, we're going to resolve this by simply insisting that we put a projection operator on the final state. That basically amounts to bleaching all the information from in here. And so that is sort of an explicit, just non-local information transfer to the outside here. And that, again, I would say there are details that need to be filled in there to make that a workable model, but it's sort of something that is worth pursuing as well. Okay, so these are there are more